Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this talk is going to be about kernel learning, random features, and dimensionality reduction, so things that we've already seen in the wonderful talks in the past 2 days. Lots of pictures, one theorem, no proofs. So kernel algorithms, as a paradigm, kernel learning tries to work with simple linear models. So whether it is classification, regression, or PCA, you end up working with the linear model. Now that is very desirable from both an algorithmic as well as a learning theoretic point of view, but for the fact that these models are usually too weak to explain real life data, so they usually underfit very heavily in every application you might think of. Okay, but these algorithms, being as simple as they are, they have certain invariances, and one of these invariances is exploited by kernel learning. Turns out that these algorithms are oblivious to how points are presented to them in the feature spaces. They only care about the pairwise inner products between the points. So what you can do is project your data to a space where it can make friends with linear models, where linear models is actually good, and feed the algorithms with the inner products in that space. That's the kernel values we talk about. Okay, so again, in all these examples you have problems that are not good with when you apply linear models to them, but if you map them to some higher dimensional space, they become amenable to linear models. A flip side to this operation is that frequently, in order to make friends with linear models, you have to go to very complex feature spaces which are very high dimensional, so that you really have to work with the kernel values. You can't work with the mapped representations. Okay, now for all these learning problems, you have in the feature space, the hypothesis is a very simple hypothesis, just a linear operation, a single operation. But since you can't work with this explicit representation, you end up working with these implicit representations, which are usually in the form of rolling sums, which are usually roll over almost the entire training data. Okay, so there are theoretical results which show that they will indeed roll over a large portion of the training data, and this leads to expensive test routines. So at test time, you get a point, you end up computing your kernel value to almost every training point before you can output the result. Now explicit forms, on the other hand, are cheaper because they don't depend on how much training data you have, so you can work with large training sets. Now this drawback of kernel algorithms, kernel learning methods, has been addressed a lot in prior literature. Some of the people who were present in the room in the morning but have left now have contributed a lot to this field, but we are going to have a different take on this, on a different solution to this problem. So recall that the whole problem starts because these vectors, these are way too high dimensional. Now the thing is, we never cared about the feature space to begin with. All we care about are inner products in the feature space. So is it possible to get those same inner products in a lower dimensional space? Turns out yes. So as Ravi mentioned in his talk, there is this very famous result called the Johnson-Lindner-Strauss lemma, which gives the existence of inner product preserving maps to finite dimensional spaces. The problem is that if you want to algorithmatize the Johnson-Lindner-Strauss lemma, all existing implementations require access to that high dimensional space. So you have to first go into that space and then come down. But that space is inaccessible to begin with in our case. So your feature space, you go to the feature space, the JL lemma tells you could come down, but you can't take this route. So is there a way out? This talk is all about giving a yes answer to this question. But for that, let's take a quick digression. And let's look at structure theorems. What are structure theorems? They are characterizations for various families of kernels. They tell us how do positive definite kernels in certain families look like. It's on top of what Professor James Mercer already had to tell us about the characterizations of PSD kernels. So for various kernel families, you have all these characterizations, and they look a bit nasty. So if you've never seen them before, no need to get worried. Since we are not going to any proofs and all, we'll be using just a simple fact about these structure theorems. All that these structure theorems tell us is that kernels in these families have a very nice form, that they are all convex combinations of a large number of rank 1 kernels. A kernel is rank 1 if its feature space is one dimensional. So it's essentially just a real valued feature which gives you the kernel. Okay, so every kernel in those 3 families I showed you is of this form. It's a convex combination of rank 1 kernel. So what you can do now is the following. Choose one of these kernels at random. You can verify for yourself that it would give you an unbiased estimate of the true kernel value at every fixed pair of points. Now, since you have an unbiased estimate, you can say, okay, now I can go back to my U statistics basics, and if I'm in trouble, I can go to Professors Huffding and McDermott, and they'll tell me, okay, if you have an unbiased estimate, all you need to do to get a high confidence estimate is get independent realizations of this unbiased estimate. And what you can do is choose D such rank 1 kernels and correspondingly get D rank 1 unidimensional features, which together give you a D dimensional feature, which I'm calling Z here. So you essentially get a map to a D dimensional feature, and that will, okay, so a little bit of learning theoretic arguments will give you this bound, that all that this is saying is that so long as your training and test vectors are coming from some bounded compact set in the original feature space, they will get mapped to points in this new d-dimensional feature space such that the inner products mimic the true kernel values very closely. So if you have seen such results before, you would know that there's a uniform convergence bound being thrown with some notion of capacity such as the covering number. So that's exactly what's going on. But what you get out of this is very nice, because what you can do now is take your training points, project them onto this d-dimensional space, train in the d-dimensional space. When test points come about, do the same with the test points, go to the d-dimensional space and test there. The advantage is that you're able to test with a unit operation in that space. Of course, you have to incur the cost of mapping yourself to this space, but it's you get faster test times, but you also get faster training routines, because anyone who has compared liblinear with libsvm would tell you that whereas liblinear can crunch through cover type in a matter of seconds, libsvm takes hours, if not more, to do the same. So, and another nice, nice in a philosophical sense of term, thing is that this mapping gives you, in some sense, implicitly a composition of these two maps. So it composes the Johnson-Lindenstrass map with the Mercer map implicitly for you, and gives you the same effect that you would have got had you gone here and then come down here. But it avoids this costly route. So in a series of very nice results, starting with a very well-cited result of Rahimi and Recht in NIPS 2007, we got ourselves such random feature constructions for various kernel families, translation invariant, homogeneous. These two can be like clubbed together because they essentially end up applying the Bochner's theorem various locally compact abelian groups. This result by Professor Jawahar is an application of these results, and this result, we kind of came up with this bit, is sort of different because neither do we use Bochner's theorem, and the guarantees are a bit more difficult to arrive at, but no point going into those details. So what you get at the end of the day are accelerated training and test routines. And if you're worried about accuracies, yeah, sometimes you do get a bit of dip in the accuracies because you're working with approximate features which may not always approximate the kernel very well. But sometimes you get increased accuracies, and that might point out to a fact that you might be overfitting with the original kernel. Okay, The flip side, well, it's not really a flip side. The nice thing about this is that these methods are task independent. Since they approximate the kernel for you, you can apply them to any kernel learning task you might think of: regression, kernel PCA, kernel clustering, what have you. But mostly they've not been applied to kernel any non-classification tasks till now. At least I don't know of any applications. It would be nice to see how do they fare with non-classification tasks. But so, as I said, task independence is how you look at it. It can be a good thing or a bad thing. It would also be nice to see how task-dependent information can be pushed into this, so that these methods become more robust to task variances across tasks. Okay. So these are some results from our paper. There are more results from the other papers that I mentioned. In all cases, you find that there are slight dips in accuracy. We have lots of variances of our We have two variants of our algorithm, so you can find some dips in accuracy at times. Sometimes you get better accuracy as well. But in all cases, you would find that you get very impressive speedups, orders of magnitude speedups in training as well as testing. Okay, so I think. Actually, I am done, and I would like to conclude here, and would be happy to answer any questions that you guys might have.